This is the one, right?
Yeah, please go ahead.
इसमें आपको ना
Please start sharing.
so you can share this with
Please start sharing.
HDMI ट्रेस कर दो डबल और दिक्कत बस
हाँ ये मीटिंग लिंक
Can you please start the presentation? I'll be there briefly.
Hello.
Yeah, please start. Please start.
Sir, am I audible?
Yeah, you are audible. Please start. Please start. You are audible.
Hey, so we are here. So please handle this with care, okay? Yeah, I mean, कहाँ से पकड़ना है? Just press करके. अच्छा, ऐसे पकड़ के बोलेंगे ना? यहाँ पर लगा इसने. But स्वेप करना पड़ेगा ना बीच में. It's okay. Just have to. You're audible. हाँ. Yeah, sorry. Telling us to start. Okay. Intro. हाँ. Try to share.
एम चाहिए आपको
Can you get started? You can do screen sharing.
बैटरी आना
Sir, we can share the slides, right? I mean, we have the access to share the slides.
Yes, yes. I can see your slides. Please start.
Can you just slides? Okay. Sir, is it visible, the slides?
Yes, 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 yes. Please start.
Sir, are these slides visible?
Yes, Ajay, they are visible. Please start.
इसको तो स्क्रीन शेयर मत कर कि स्लाइड शेयर कर. प्रेजेंट मोर और विंडोज शेयर.
And
Yeah. So now,
open करवाए
perfect. हाँ.
ये हमारे नोट्स दिख रहे हैं इसमें. प्रॉब्लम क्या है? कुछ
इसको एक्सटेंड करिए.
हाँ, ये प्रेजेंटर मोड में चालू करो ना इसको.
एक्सटेंड करके करिए. प्रेजेंटर मोड ऑन.
क्या क्या?
कैसे?
आपने डुप्लीकेट किया होगा शेयर स्क्रीन में.
Screen.
शेयर स्क्रीन में
पूरा स्क्रीन दिखता है
पूरा स्क्रीन दिख रहा है बताओ.
ऑप्शन होता है एक्सटेंड करो कि डुप्लीकेट करो. इसमें एक्सटेंड करो और
Sure.
प्रेजेंटर मोड.
Window. One sir. Only this. Right? Okay. Okay. Hold on. Only this, right? One sir. Yeah.
हाँ
This.
ये. ओके.
मैं यहाँ पे
स्पीकर नोट दिखनी चाहिए ना हमें तो.
And then you can.
ये रीड में देखो गाइड में से.
अरे इसको इसमें खोल लेंगे. ठीक है.
You can start now.
Yeah.
Sharing stop around. Screen share. Okay.
I think please start. Why are we dealing so much? Please start.
सर स्टार्ट करना बोल. ये में लिखते हैं.
You take.
नितिन उसको टैब करिए. ये रैंडम से
पहला तेरा है ना?
हाँ इंट्रोडक्शन. ठीक है मैं सो
बोल सकता राजा.
Good afternoon, everyone.
He present.
Just 2 minutes. Hi, everyone. I'm Nitin, and he is my team member, Ravi Shankar. Today, we are here to present two papers as a part of our seminar.
So the first paper, hello. The first paper that we're going to present is the influence selection. So the first paper we are going to present is the influence selection for active learning. So this paper was presented at International Conference for Computer Vision in 2021 and written by Zoing, Louis, and his team. The main goal of this work is to reduce the cost of data annotation using new active learning approach that works with any model and any task. It helps machine learning model learn efficiently by selecting the most valuable data points for labeling. So next one. So the problem statement is like in this it's the active learning it's like the selecting the right data to label is crucial, like as we know, is crucial for improving model performance. However, the existing methods have several limitations. The first is the uncertainty based, like model can be over, like if we give the the like if we train the model can be overly confident in incorrect predictions, like if we train it over the incorrect samples that are not valuable, so it will lead to poor sampling choice. The second is the diversity based selection, and the problem in this, like it is very computationally heavy, making it inefficient. And the annotation bottleneck is like labeling data is very expensive and time consuming, especially for object detection. For example, like in Coco dataset, the images can be contain up to 63 bounding boxes, and significant increasing the annotation cost. So uh, this paper address these challenges, and we aim to develop a method that work across different tasks and models and selecting the most valuable samples. So this paper introduce a better way to pick the right data for training. So the main algorithm in it is ICL algorithm, and its implementation untrained, unlabeled unlabeled on over unlabeled data sets. So we will explore these in upcoming slides. So the main function used in this wallpaper is the influence function, which is actually developed for statistics by Cook in 1982. So this the first the LJ the first it's the gradient of it's take the gradient of the loss function by gradient of the loss function, then applied the Hessian inverse matrix to it. So here the loss function the hmm, so he, the loss function is calculated after the new parameter introduced in the validatory set, and the Hessian matrix is like restrictive factors, like it will uh, it will adjust the it will adjust the gradient. Like if it's already trend, then the small improvement will not improve that much, so it will adjust that factor. Then the innovation of UUIC, so unlabeled. The first we will start with a small very basic model, then we will introduce him the unlabeled sample, and we try to classify that, and then we will calculate the gradient of the loss that loss over the introduction of that new dataset point. Then we will calculate the influence calculation. basically the first like using the old function, and here R is the validatory data set that is already classified. So the mo- uh, so the next the ICL algorithm workflow, it's working like this. The uh, so first we have the very small model U naught, then we will introduce the small S naught or train, introduce a parameter, then we will make a model M1, and then we will calculate the influence factor of that, and if it's improving, giving us a good result, then we will keep that parameter in that model and we will name it M2 and move on. But if sir, it's like it's written here because we are not directly calculating the Hessian inverse, as it is very computationally heavy. Instead of that, we are calculating some using different technique like yes sir, that's no. So it's describing, but I don't mention here.
Producing something with no connection with the slide. Like that's avoiding Hessian inversion here.
Sorry, sir.
So what do they do to avoid the Hessian inversion?
Sir?
What do they do to avoid the Hessian inversion?
So they do like H of HV, and this is some CFG. Actually, I don't remember this. So we will, so like we calculated the S test, and like if it improves significant to our model, then we will name it the next model, and we carry out this till we attain a certain accuracy or good till we arrived at good model. So the more the negative influence is like it's better for us. If the model is already at a good level, then it will not give the significant negative result. So here are the experiment results. It's the data set we used is this CIFAR 10 and CIFAR 100 and SVHN, and here we come. So we first taking the it's like what?
I mean, the approximation to Hessian inversion and avoiding the inversion, both of them could have. That is not specific, right, to Isol's innovation. What are the? Can you analyze in some more details?
So like we are taking the, so what, I'm not getting what to explain.
What is the difference? What are the differences?
No, so it's implementing directly that same thing. It's first applying to the ZZ that we calculated when by introducing a new data points into the validity set. Then we are adjusting that how much it's like. If it's already trained, then it will the Hessian is like restrictive factor. It will, if it's already good model, then it will not increase that much. But if the data point introduced have significant impact, then it will be reflected in that model. And then we are taking the dot product of already achieved loss function and the influence of that new introduced one. So it's like calculating the impact of the new point over the old.
Traditional influence is also that. So what is the difference in ISIS? What ISIS innovation is?
Sir, it's the means.
Are you clear about what the innovation is?
Yes, sir.
What is innovation?
मतलब
So it looks like you're not clear, right?
sir, I'm not able to explain clearly.
But then,
So I have done this paper and
doesn't mean each other.
but we
Discuss the pros and cons of the.
The pros and cons, but I'm still not understanding what is the innovation. How can you discuss pros and cons for this? What is innovation? You have unable sample set, right?
yeah.
The influence function is based on subset. Now, is the only innovation that you have used pseudo labeling? That's it. That's the only innovation.
Sir, मतलब
Is the only innovation that you have done pseudo labeling. And the expected gradient part is also not explained here because expected gradient with respect to that one pseudo labeling, right? The
so
expected gradient with respect to the pseudo label. So it's not really expected, it's some point estimate. It's not expectation with respect to the expectation also point estimate. But I'm saying it is there's no distribution on which you're really taking expectation. Expected is used very loosely here.
So it's like the like we have a validatory set and we have a loss function for that, and then we are taking the dot. We are taking the influence of that new introduced on that loss function, new introduced data point on that.
That is what traditional influence was doing, right?
Here for the data point.
So influence is taken from statistics as
Here for the tunnelable data point, a pseudo label had been created using that function. And
so is that the only difference? That's what I'm asking.
Yeah, based on the function, it was the only because the gradient of that expected, the gradient of the data point with its pseudo label had been considered for calculating the influence, and that gradient is making difference compared to the traditional equation.
There's a little bit of inconsistency. So you had an IZ, and influence calculation is IZ prime comma R.
so basically
R suddenly here.
R is the already the validatory set.
Validation set.
Yeah.
Yeah, I think you have not defined validity. There's no definition, right? There is definition of validation. And then suddenly here, that GZ prime, see dimensionality also has a mismatch. You have taken gray. So the influence is a quadratic function, it's a scalar, right?
Yeah.
It's an R. Whereas what you've written to traditional influence functions, it will be a vector. Hessian inverse times a gradient. It's a vector. The more negative IZ, so influence calculation gives you a scalar. The more negative that scalar, the more beneficial the sample.
Yeah.
But then there's a mistake possibly in your expression is written at the top. So that is a vector. Traditional influence function.
Yes, sir.
Hessian inverse is also a matrix.
Hessian matrix.
So IZ in the traditional influence function is a vector which equals a matrix inverse times a vector. You understand dimensionality. So that is the traditional one is a vector. This is a scalar. What is the difference? In fact, I don't even know what you mean by
the traditional one is scalar. It is a influence of the data point Z.
Data point Z.
But minus H theta inverse into a gradient is a matrix times a vector is a vector. How can you call it a scalar? Hey, come on, I mean, you please. How can you say that's a scalar? It's a vector, right? So you need to be very thorough in your presentation.
Yes.
This is talking.
Yes, sir. Sorry, sir.
I don't understand what this ISA's innovation is other than pseudo labeling. Pseudo labeling is what you've done some pseudo labeling and that they used to extrapolate. Nothing else I see it as the innovation.
So by introducing new points, we just checking like it's influencing our. So it's just a formula we have that they have used.
Sorry. Syntactically, there is a mistake. Comparing a vector against a scalar, it doesn't make sense. You're not able to explain it. I don't know what to make of this. Go ahead.
So this is the result.
Spend some time reading.
Yes,
It's like a very last minute. How much time have you spent?
sir. 3 days.
This is a seminar, a course seminar. There's significant weightage for this. Do you understand? Please do justice.
So this is the experimental result for classification. For this, we use the data sets like CIFAR-10 and CIFAR-100 and SVHN, and we compared it with random and three methods. Like one is randomly picking the new data point, and the other is the corset, and third is the ISL. So for the random result we are taking as a baseline, and the corset is improving its 12% in the CIFAR-10 result, and ISL is improving its 23%. So here are the graphs. So it was just used there. I didn't.
That's what happens if you do last minute preparation. You have to think through it. All of this presentation. This looks like someone else's presentation. We are just speaking. Go ahead.
And similarly, the experiment result for detection also, the dataset used it VOC 2012 and COCO, and the key result is like the ICL algorithm will reduce the. We are able to achieve that accuracy with 30% fewer boxes than corset, and in COCO dataset we are able to achieve in 16% fewer boxes than random, and for large scale it's saving the 8% saving. That's
Get lucky with one random. Is it average across multiple?
yeah, it's average. It's whole
And what's the standard deviation?
standard deviation.
If it's 16% fewer boxes, you should have some standard deviation.
So, but it's.
By the way, others can also ask questions.
So the finally the like we tested like the paper tried testing with a different experiment. So the first is by with and without Hessian. Like if we don't apply the Hessian there, so without Hessian it will be for 5,000 samples. It will present the accuracy of 81.24. And without that it will be 80.54. That's not, that was difference. The and the reference it, for the reference, the validation, these are the results only.
Which number of samples that is?
Yeah. So for 1000 samples, like by case, like picking up the top, yeah. Uh, So this is comparison for when we run for 1000 samples.
So I want to present today about the paper data pruning via moving on sample out. So it is a NeurIPS accepted paper in 2023. Before that, there are two limitations from the literature in which there are hard samples which are noisy or outliers which make huge losses, and because of that, it is very hard to distinguish uh, which are important samples, and these giving strong signals are unnecessary. And another limitation is model dynamics are rarely considered for subset selection, because for every to select a subset of data points, always a converged final model is considered, but the intermediate training steps are not considered, so which causes to avoid the data points which are used in the early stages of training. Uh, so this is the problem statement for this paper. So how to select a subset of data set that helps the model to learn and perform better with lower computational and storage resources, and addresses the limitations that are presented in that are present in the past methods. And the approach is they had proposed a data pruning approach, which is called moving on sample out. It considers model dynamics for sample selection, and it is a optimization based method. So in data pruning, there are three methods: uh, selection by important criteria, and diversity-driven approach, and optimization-based approach. And this is the optimization-based approach. Before I go to method, this is the method background I want to present. So they focused on classification task in which that whole dataset contains two x and y, in which x is a real vector of n dimension and y is a one-hot label coding, which is done from the underlying distribution P. And this is the optimization problem that they are trying to solve, in which it is the estimation of the so they are trying to minimize the empirical risk uh, over the empirical risk of the data point Z. And this is so this is done across all the data points in the D, which is a subset of set S, where L is the cross entropy loss function, and S cap is the final optimal data set subset selection. And this is a rough idea of what the method that I'm going to explain. And for WD star is the network parameters trained on data D using SGD optimizer. No, this is the basic optimization problem that I'm going to show in the next slide. So they had considered so there is the term empirical risk, which is the average loss of the model or network which is achieved on the training set, and pruning ratio is the ratio of the data samples which had been removed from the data set to the ratio of to the total number of samples. So this is the main they had introduced a score to segregate the model, so to segregate samples based on segregate the samples based on their information or importance for model learning. So Moso score for a specific sample Z, this is the method that they had used, which is the difference between the average loss made by the model which is trained on the data set excluding the Z over the dataset excluded by Z to the average loss made by the model which had been trained on the whole dataset. And where's
W star
is the trained parameters of the network which is on whole data.
the same set.
Yeah, loss is on the same set. Yeah, loss is on the same set because it can't be a good comparison. But there are limitations to this method. So I want to conclude. So when it sample Z is important, when it is trained, when a model is not trained on that sample, uh, the model is unable to learn better. So the loss of the model, the loss of the function on the dataset S excluding Z is more. making the Moso score greater than 0 based on the before expression. While if Z is unrepresentative, it doesn't make any impact on the empirical risk made by in the both loss terms. If Z is harmful, it is decreasing the performance. It is harmful to the model, making the increasing the empirical loss in the second term by making by making the Moso score negative. So a sample which is important has a positive Moso score. But it has it has a limitation because it is quadratically related to the number of samples in the training set, making it very infeasible for the larger data set. So what is the method that they had proposed in this? Yeah. So yeah. So for approximating that value, which is a retraining approach, instead of that, they had presented an efficient approach, which is gradient-based approximator, in which the approximation is done using the gradients, which is the inner product of the average loss, inner product of the uh, empirical risk of the model on the dataset excluding Z to the gradient of the sample Z. So where the WT and eta t are the series of parameters and learning rates during training, and yeah. So yeah, I will explain this. It is an estimation across all the time steps. Instead of, it addresses the limitation. It addresses the second limitation that I had presented before, because instead of later stages, it is taking the whole time steps into consideration. So the intuition is if the gradient of the sample Z is consistent with the direction of the average loss, so they are in the same direction, and selecting those samples which are in same direction as the remaining samples uh, is can make the model learn better without much diversity. And this is the basic assumption that they had took in remaining samples. Yeah, not all the samples, but they are trying to select those samples which are in a consistent way. Yeah, gradient has to be in different directions, but when the gradients are in different directions, the model is unable to find the pattern better, because there are outliers which make huge losses and send very strong gradient signals back propagating to the weights, and it is changing the behavior of the whole model, and which is the reason that they thought that it is decreasing the model's performance. And this is
The validation data should ideally tell you
Hmm.
if the alignment is going to be helpful or not.
Yeah, there are results I will present. There are
Yes, is itself noise.
yeah, and
If I want the Z to be different,
there are
current parameter. So there's an assumption also.
Hmm.
Before
Yeah.
noise.
Hmm.
What I meant is, if the current set of weights are wrong,
Hmm.
misleading,
Yeah.
then gradient would also be misleading, right?
But it is taking average across the time steps. Yeah, it is the estimate expected. Yeah, and there is an assumption, there is some limitations to this method I will present afterwards, because so if the number of important samples in the data sets are less than the noise, then this method may not work. And it is an assumption that they took that the number of important samples in the data sets are larger than the noise. Indeed, it is a basic assumption that they took. And their intuition is, if the gradient of sample Z is consistent with the average gradient vector, then we are selecting samples. Yeah. And if Moso score is higher, then it is important and representative sample of the whole large data set. And this is the algorithm. So initially, we have the data set and the pruning ratio with us. And the initial weights are randomly initialized. Uh, and so if you have parallel computing, then the data set is partitioned into I subsets, where I is the number of devices. So the weights had been calculated using the SGD optimizer, weights and learning rates, and they had been considered, instead of the raw weights, they had been considered time to time for Moser score calculation for expected Moser score calculation. And after all subsets had been considered, there will be all the Moser scores will be merged, and the samples with the least Moser score will be avoided for the subset selection. Stochastic average. Yeah. So yeah, for a subset on each device will be considered separate. So the assumption is the subset should no, they are disjoint. Yeah, and each subset should represent the large data set and should be large enough to conduct this task. So when a data set is considered in a subset which is on one device, it won't be considered in other subset. This is the so we have S1 to Si, which are yeah, we can take overlap, and we can also take average of those samples which are intersection of low overlaps. But the method that they had presented is they didn't take an overlap of data points. P? No, T is the maximum number of training steps. No, it is not a moving average. T is maximum. So yes, a small t. Small t. So can you repeat the question?
It's a moving average, right?
Yeah.
Average keeps on shifting. Dropping one, adding two. Dropping one, adding two.
But instead of time step, they are considering all the time steps, right? 1 to t. They're taking expected time. Yeah. No sliding into it. It is considering all the time steps across the time steps. So to have average across all the time steps. And after that, it will be merged into a subset, and pruning can be done based on the pruning ratio which had been mentioned before. So yeah, this is the parallel computing method that they had proposed, in which number of samples removed depends on the pruning ratio, and the underlying assumption is that every subset on is the number of subsets, there is a marginal increase in the performance, and it is due to that if the it is easy to get the sensitivity of the sample when the data set is small based on that data set. But they didn't presented how many subsets or how many times that they had done this experiment, so to whether they are getting consistent results or not. But they presented 1 point by using the brute force retraining leave one sample approach and the gradient approximation method that they had presented in this paper. And we can see that the error between the true and the approximation is at most related to the uh, upper bound of the gradients, which is g, and it is quadratically related and linearly proportional to the number of training steps. So as we increase the number of steps, there can be a huge error in approximation. So small number of training steps had been considered. It's taking a trade-off between the accuracy and this error. And also there is a upper bound to gradients which can be reduced by clipping the gradient. It is a method, but they had not presented anything about the gradient upper bound. And the complexity analysis is it takes the linear time with respect to the number of data samples in the number of data samples, which is while the get 1K data set, and um, the GPUs that they had used is Tesla V. The model they had considered, the network they had considered is ResNet 50, 50, yeah. And the baselines are random sampling, heading, forgetting, grad, and D, L to N. Yeah, I have a normal idea. I didn't gone through deep into it. So heading is, yeah. I don't read, but heading is selecting data points which are close to data points are close to each other in the feature space in higher dimension, and forgetting is forgetting is
Yeah, go ahead. Go ahead.
so the dataset had been selected using ResNet architecture, and the dataset had been used to to understand the performance across different models, and the models that are considered as SCNet and EfficientNet. They both trained on subset selected and is able to outperform the methods. Is able to outperform other methods
I see.
using this approach.
Consistently across.
Yeah, consistent. And taking a computational efficiency.
Yeah, but then it has an inflection point. It can only work when the data set is very large.
Yeah.
So I don't know what is the value of active learning with large data set. So little contradictory, right?
Based on the data set, the data set, it may vary.
So this, yeah. So then they should have some experiments on basically compare against core sets. They have not compared against core sets.
Yeah.
So they are in a different league, large data sets, but then they are comparing against active learning approaches. So it's not fair. I mean, I feel. So can you go to the project description? So what is your project description? I think that's a question.
So we have a data set of having 16 tasks, which each of having 6.5K samples. So the data set is very large, and we are trying to retrieve 20-30 tasks from the data set. Just this is our.
So then your active learning is not your goal.
No.
So then. Next team can start. Yeah, continue.
Data extension is the key of the task.
Mm.
That is the basic project, and that's why the data is also decreasing.
Ajay, can you help them? Can you help them set up? That same laptop or different? Thank you. So should I be, grading both of you separately, or are you one team? Because there was a difference in the quality of presentation, very honestly. Team, okay. Then you should help each other.
Yeah.
If you're a team, then you should talk to each other.
Yeah.
Ensure that the other person's presentation is in sync. You can't say, I don't know what the other person is prepared. Then you will be penalized for the other person's lack of thoroughness. So please, everyone knows this, right? If it's a teamwork, you should hear out each other. I mean, You can't be just presenting in front of me for the first time.
वहाँ पर इसे मिल